In this section, we're going to learn how to integrate with respect to y, and what it's going to do is help us to find area of certain regions that would be hard doing it the way that we've learned. And we're also going to learn how to find volume of a solid that's rotated about a vertical axis, and that could either be the y-axis or any other vertical line. So first, a quick review of what we've already learned about area. If we want to find the area between two graphs, say g of x and h of x, we look for a consistent upper and lower bound. So no matter where I draw a vertical segment within this region whose area I'm finding, the top of that segment will always be on g of x, and the bottom part of that segment will always be on h of x. So I have a consistent upper and lower bound all the way from a low x of a to a high x value of b. That x interval of my region then becomes the limits of my integral, and I simply take the top curve and subtract the bottom curve, and I'm doing this integration with respect to x. So notice that everything in this integral references x. From the limits being the x interval, these functions are in terms of x, and I have a dx sitting at the end. Let's take a look at another region that causes problems with this method that we've been using. What made our usual method work so beautifully was the fact that we had a consistent upper and lower throughout our entire region. But if you take a look at this region I've highlighted in yellow that's bounded by the graphs of h and g, I look okay in here because g is my upper and h is my lower. But when I'm in this region over here, notice h is both the upper function and the lower function. So I start to run into some issues with how I did it before. But if I look at that same region and I just consider a right versus left boundary, you can see I have a consistent right bound and left bound. The graph of g is always on the right, and my graph of h is always on the left. So what I can do in this situation is integrate with respect to y. So what that means for us is we have to turn this integral to reflect y. So everything will be from y's perspective. My limits are going to be a y interval, so I'm going to go from a low y value to a high y value. In my integrand, I'm going to have functions in terms of y. So my functions will say x equals h of y, x equals g of y. So you want them solved for x instead of y. And here at the end, this is going to say a dy because that is my variable of integration. And here's what it looks like is an integral. Let's take a look at a couple of examples. In this first example, we had actually done one of these before. We had integrated this with respect to x. And what we had to do was split it into two regions because we had a change in what the upper bound function was at that intersection point. So what we had to do before was write two separate integrals for this one, and we had to change it right here because my upper bound on the left side was the red function and on the right side was the blue function. But if I look at this sideways, so I'm doing horizontal lines instead of vertical, you can see that no matter where I draw this horizontal segment, the red one is on the left and the blue one is on the right, which means I can find this area integrating with respect to y, and I can do it with one integral. The first thing I look at are my limits. My low y is 0. My high y is that 1.407. In my integrand, I have to do the right minus the left, so the blue one is on the right. I have to have these solved for x so that they are in terms of y. So each one of these, I'm going to solve for x. And now as my integrand, I just do right minus left. Because I solved these for x, everything here is in terms of y. I have a dy at the end, and now I just plug this into my calculator to get my answer. If you were to find this area using our previous method, by splitting it here and doing two separate integrals, you would find you would get exactly the same answer. Let's take a look at another example, and this is going to follow what you'll need to do in Delta Math on this one. In part A, I'm asked to find this area by integrating with respect to x, and in part B, integrating with respect to y. The first thing I need to do with either of these is find these intersection points, and since I'm looking ahead to part B and I have to do this in terms of y, I'm going to pull up the x and the y values for these intersections and store them. I went ahead and found my intersection points, and I stored them into my values, and I mentioned the values over here where I'm storing them. So in this part of the problem where I'm saying what my intersections are, I just used A, B, C, and D because I had already defined them. So if I'm integrating with respect to x, then I'm looking at an upper minus lower situation. And I can see I do upper minus lower from a low x value of 0.158 to a high x value of 3.146, and that gives me my limits. And then I just do upper minus lower, and I can see my upper curve is the red one, which is f of x, and the lower one is g of x, which is the blue one. Putting that in my calculator gives me an area of 1.949. The next part wants me to write an integral to find that area in terms of y. So now I'm going to look at this from left to right. I can see my limits are going to go from this c to d, so those y values of that region. I'm going to do right minus left. So my integrand is going to be formatted the blue one minus the red one. But before I put them in, I need to solve them for x, in other words, get them in terms of y. Solving each of these equations for x puts it in terms of y, and now I'm ready to write my integral. So my integral is formatted low y to high y, and then my graph on the right minus my graph on the left. And if you plug this into the calculator, you get 1.949, which matches what I got in part A, because the area of that region is its area. It doesn't matter which method you use. Some problems are easier to do in terms of x, and some are easier to do in terms of y. In the next part, we're going to look at some more rotational solids. This time we're going to rotate about a vertical axis, which is going to lead us to integration with respect to y. Again, I'm going to take a bounded region. I'm going to spin it around, this time a vertical axis, in this case the y-axis. It's going to create a three-dimensional figure for us. And what I'm interested in are the cross sections. So when I look at my completed figure here on the right, I can see that my cross sections perpendicular to the y-axis are circular. The radius of each one is different depending on where that cross section is drawn, but I can see that that radius is defined by this graph that's here to the right. Because I have circular cross sections, I know I'm going to use the disk method, which is simply just pi r squared. And you can look here and you see your pi. This right here is our r squared, just like before. Because I'm integrating with respect to y, this whole integral is about y. So it's a low y to a high y are my limits, and my function that's here is solved for x, so that is given in terms of y, and then I have a dy here at the end. Like we talked about before, if our region is flat against that axis of rotation, that's going to lead us to this disk method. And if we have a gap in between the axis of rotation and the region, that's going to be a washer method, and you see that reflected in this second group of pictures. You can see in this picture that my cross sections are washers, and when I have a washer, I'm going to have an inner radius and an outer radius. The inner radius is the graph that I hit first, so as I move from the axis of rotation, whoever I hit first is going to be my inner radius, and as I continue on, whoever I hit second is going to be my outer radius. This will work exactly like our washer method that we did previously. The only difference is we're doing this integration with respect to y, so our limits are going to go a low y to high y. We're still going to have to make that adjustment for an axis of rotation that is away from x equals 0 or the y-axis. And then we just take our outer radius squared minus our inner radius squared, which is that same washer method that we used before. Let's take a look at a few examples so you can see how this works. In question 3, we're going to take our region defined by square root of x, y equals 2 and x equals 0. We're going to revolve it around the y-axis. I can see from my picture that my cross-section here is a solid circle, so this is going to be a disk method. I saw that coming because my shaded region here was flat against this axis of rotation, so I knew it was going to be a disk method even before I drew that picture. Here's my general formula for the disk method, pi r squared. I'm doing this with respect to y because I have a vertical axis of rotation. And my limits are going to go low y to high y. So when I look at the shaded region, the lowest y value is a 0, and the highest y value is a 2, so that gives me my limits. For my radius here, since I have a dy, I need this to be in terms of y, so I need to solve it for x by squaring both sides. Solving that for x gives me y squared, so y squared is what belongs here in my integral. All I have left to do is put that in my calculator, and it gives me an answer of 20.106. In our last question, we're going to take our same region as before, but this time we're going to rotate around x equals 4. When I see this gap that's occurring here between my region and my axis of rotation, I know I'm going to use the washer method for this. And because this is a vertical line of rotation, I know that this is going to be a dy, so everything is going to be from y's perspective. As I start setting on my integral, I know my limits are going to go from 0 to 2, so low y is a 0, my high y value is a 2, and I'm going to have to do outer squared minus inner squared. So let me figure out who inner and outer is. As I start at the axis of rotation and move toward my shaded region, I hit this graph first. That tells me that is inner. And as I keep going, I hit x equals 0. So that means that one is my outer function. And I also need to account for the fact that my axis of rotation is at x equals 4 as well. So I'm going to start with my outer, which is x equals 0. I'm going to subtract my axis of rotation. And then I take my curve that's rotating on the inside, which is y squared, subtract my axis of rotation and square that. And when you look, my integral just says pi, my outer radius squared minus my inner radius squared, and then dy because I have this vertical axis of rotation. Putting that in my calculator gives me my final volume of 46.914. And again, just be careful of those common mistakes. Remember to put the pi in the beginning. Remember to square each one of these. And remember, if this is a dy, if you have a vertical axis, you need everything from y's perspective, from the limits, and these functions need to be solved for y. And don't forget to subtract your axis of rotation. Lots to remember on that.